Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asgar, and today the topic of our discussion is characterization of pharmaceutical materials by thermal analysis under the subject of thermal analysis. Dear student, so far we have discussed some of the important applications which were uh, discussed by thermal analysis. For example, we have studied the thermal analysis of many inorganic materials, while we have already also studied the thermal analysis of metallic materials. Moreover, in last lectures we discussed the phase transitions materials, and we also discuss how we can find phase transitions by using thermal techniques. The most important thermal techniques that we have studied was diffraction scanning calorimetry and TGA thermogravimetric analysis and diffraction scanning calorimetry and DTA diffraction thermal analysis. These thermal techniques would help us to find out the different hidden properties that would present in any material. So thermal analysis is quite useful technique for the study of different properties, for the study of different uh, potential applications of materials. In this lecture, we will discuss the some of the characterization of pharmaceutical materials by using thermal analysis. Thermal analysis actually has been an extremely important analytical technique within the pharmaceutical industry for more than 40 years. So it's about not a recent technique, but we are using it since 40 to 50 years. Although the technique could easily be classified as mature, and recent advances in diffraction scanning calorimetry have generated renowned enthusiasm in thermal analysis from pharmaceutical point of view. These new developments include T0 diffraction scanning calorimetry and modulated diffraction scanning calorimetry, which provide significantly improved performances in critical areas. For example, sensitivity, resolution, and separation of complex transitions. This lecture would probably illustrate the use of these improved diffraction scanning calorimetry technologies on the characterization of wide variety of pharmaceutical materials, including amorphous and crystalline drugs. Moreover, drug delivery systems such as tablets, biodegradable polymer, microspheres, proteins, and frozen solutions used for freeze drying. So that would help us to actually evaluate the different types of pharmaceutical materials, either they are amorphous or crystalline in nature. Moreover, it would also help us to study the drug delivery systems, such as in the form of tablets, and moreover, it would be helpful for us to understand the biodegradable polymer, microsphere proteins, and frozen solutions used for freeze drying. So, recent advances in diffraction scanning calorimetry. We will discuss a brief description of the new technologies which is provided to help to explain how the improved performances would be obtained over traditional diffraction scanning instrumentations. So far, we have discussed the many things about the traditional diffraction scanning calorimetry and somehow the thermal analysis techniques in for the characterization of different compounds. Now, in this series of lectures, we will definitely discuss some of the uh, perf- uh, performed and recent advances in diffraction scanner calorimetry. First one is actually the modulated diffraction scanning calorimetry, modulated DSC. The modulated diffraction scanning calorimetry experiment actually can performed on same instrument as used for traditional diffraction scanning calorimetry measurements. The difference between the two techniques is in the temperature profile which is applied to the sample and deconvolution, which is deconvolution means it is the separation of the resulting heat flow signal into several components. Instead of simple linear temperature change used by diffraction scanning calorimetry and modulated diffraction scanning calorimetry uses two simultaneous heating rates, an average or underlying rate similar to diffraction scanning calorimetry plus a sinusoidal or modulated heating rate. So these are the two simultaneous heating rates, which is an average heating rate, which is quite similar to the conventional diffraction calorimetry, while the sinusoidal or modulated heating rate, which would be used for the modulated diffraction scanning calorimetry. The average rate provides information equivalent to traditional DSC, while the modulated heating rate provides unique information about the sample's heat capacity. This figure 1 is actually shows how temperature changes with time in a modulated diffraction calorimetry measurements. Actually, this is the kind of experiment we can see in this picture 1. As described previously, the reason for applying simultaneous heating rates is to create additional information about the heat capacity or structure of the material. A brief examination uh, of the equation used to describe the flow signal from a DSC or modulated DSC experiments shows the benefit of dual heating rates. dH is divided by dt is equal to Cp dt over dt plus FTT. Whereas dH over dt is actually the total heat flow due to the underlying or linear heating rate, while the Cp is actually the heat capacity component of the total heat flow and is calculated from the just of the heat flow that depends on the modulated heating rate. As you people remember in our last lectures that in phase transition materials, exploration of phase transition materials, I have discussed the Cp, which is actually the heat capacity component of the material. Cp would also help us to find out the Curie temperature of the material. It gives us an information of phase transition point, and it would also help us to collect the crystal structure of that particular sample uh, below and above the phase transition point. CP is uh, quite familiar and quite important to discuss the diffractions calorimetric results. It actually verify the diffraction scanning calorimetric results along with the uh, dielectric measurements. While in the question, dt over dt is actually the measured heating rate, which has both an average and amplitude component. While FTT is actually the kinetic component of the total heat flow, and calculated from the difference between the total and heat capacity component. While Cp dt over dt is actually a reversing heat flow component of the total heat flow. Traditional DSC diffraction calorimetry actually provides a single signal, which is the sum of all thermal events occurring within the temperature range of experiment. This often makes it difficult to interpret the data or detect small phase transitions. While modulated diffraction scanning calorimetry has a significant advantage over the traditional diffraction scanning calorimetry. It measures both the heat capacity component while total and obtained kinetic component from the difference. So that would be the huge difference that occurred between the simple traditional DSC and modulated DSC. Separation of complex transitions into specific components greatly improves interpretation of results. In general, modulated diffraction scanning calorimetry provides the following advantages over traditional DSC. Number one is the increased sensitivity. Number two is increased resolution. Number three, separation of complex transitions. Number four, more accurate measurement of crystallinity in semi-crystalline material. While the fifth one is the direct measurement of heat capacity either while programming temperature or holding it isothermal. These are the actually some of the key differences that is established between the conventional or traditional diffraction scanning calorimetry and the modulated diffraction scanning calorimetry. We know that traditional DSC actually provide only a single signal, which is actually the sum of all the thermal events occurring within the temperature range of that particular experiment. So it provides us only one information with single signal, and we have to set the temperature range for a particular material. How we can set the temperature range for for every compound? Yes, first we need to find the properties of that material in a range of temperature. The temperature range may vary from 100 Kelvin to up to its melting point. So we need to find that particular position or the temperature range from where we want to we want to interpret the data of diffraction scanning calorimetry. So in the case of traditional diffraction scanning calorimetry, it gives us only one single signal, which is actually the sum of all the thermal events. While in the case of modulated diffraction scanning calorimetry, it has a quite significant advantage over traditional DSC, because it measures both the heat capacity of the component and total kinetic component from the differences. So that would help us to give a more obvious information, more advanced information of that particular compound. While here is the increased sensitivity, increased resolution, separation of the complex transitions, more accurate measurements of crystallinity in semi-crystalline material, and direct measurement of heat capacity either while programming or holding it isothermal is an over advantages of conventional DSC. Some of these benefits are actually we have discussed and drawn on the and will discuss on pharmaceutical materials later in different next lectures. Here is the actually T0 diffraction scanning calorimetry technology, TDSC technology. Until the recent introduction of this new approach to measuring absolute values of heat flow, DSC technology had not changed in a significant way since its commercialization in the mid of 1960s. That technology actually based on a single differential measurement and used either as a heat flux or power compensation approach. The performance limitations of those early technologies could be seen in baselines that were neither flat not very reproducible, while in peak widths that were much greater than expected from the melting of pure metals. T0 diffraction scanning calorimetry technology actually provides us very significant improvements in baseline performance, sensitivity, and temperature resolution of transitions. The improved performance of T0 diffraction scanning calorimetry results from a cell design which produces two simultaneous differential measurements and provides for the ability to calibrate the thermal resistance and heat capacitance of the individual sensors as a function of temperature. We know that actually whether it's conventional diffraction scan calorimetry or T0 DSC technology, it is actually depends upon the heat capacitance and thermal resistance of the sensors as a function of temperatures. By knowing the actual thermal characteristics of a specific cell, any imbalance in capacitance or resistance of the sensors can be accounted for the calculation of the absolute heat flow signal. The improved resolution of T0 diffraction scanning calorimetry technology can be seen in this figure 2. A comparison of indium salt, indium melt with traditional and T0 DSC technologies. T0 diffraction scanning calorimetry provides a much more accurate heat flow signal than was previously available. Because of this, heat capacity values can be measured in a single run versus the 3 runs required for traditional diffraction scanning calorimetry. This kind of performance results directly from much more complete calibration of the physical components. It is actually the components of the system, and use of these calibrations values in calculating the heat flow due to just the sample. Moreover, calibration factors are measured versus temperature and then continuously applied to four-term heat flow equation, and it would be help us to calculate the sample heat flow. We have already discussed this formula to measure the total heat flow, which is due to the underlying or linear heating rate. Moreover, the real advantages of T0 diffraction scanning calorimetry technology are illustrated. I will discuss on pharmaceutical materials in applications point of view. In general, benefits fall into 5 major areas. Number one, it would be benefited, number one, as a flat and reproducible baselines. The number two would be the higher sensitivity. Number three is the higher resolution. Number four, single run measurements of heat capacity. While number five is the higher heating rate modulated diffraction scanning calorimetry. So these five benefits of modulated diffraction scanning calorimetry actually would help us to replace the results of conventional diffraction scanning calorimetry. We know that the conventional scanning calorimetry only provides uh, one single signal, which is only the sum of all kind of thermal events occurring that within that particular temperature range. While this modulated diffraction scanning calorimetry is actually the combination of heat capacity component and total, and obtains the kinetic component from the differences. Separation of complex transitions into specific components greatly improves the interpretation of results. In general, modulated DSC provides many advantages over traditional diffraction scanning calorimetry. For our knowledge, I would like to explain the advantages of modulated DSC over the traditional DSC. The it have increased sensitivity. Moreover, it has increased resolution. Separation of complex transitions is quite easy in modulated diffraction scanning calorimetry over the traditional DSC, because modulated DSC would help us to scan the materials in wide temperature range with more sensitivity and increased resolution. More accurate measurements of crystallinity in semi-crystalline materials, while the direct measurement of heat capacity, either while programming temperature or holding it isothermal, is actually the advantage of modulated diffraction scanning calorimetry over traditional TSC. This is all about this lecture. Thank you very much.